Okay, in today's video we'll be discussing this epic photo and how it was taken. The photograph, taken by a satellite's camera on July 16, 2015 from 1 million miles away, depicts the fully illuminated dark side of the moon transitioning to Earth during its 27-day orbit. The dark side is just what we call the side of the moon we don't see from Earth due to its tidal locked position. There really is no single dark side since the entire surface of the moon actually gets its share of sunlight during its month-long phase cycle. This very popular photograph has been shared all throughout news articles, science social media groups, as well as flat earth debate groups on Facebook and other social media sites. The photo is actually from a series of photos taken by a system called EPIC. EPIC takes snapshots of Earth every 2 hours, and you can view these photos near real time on its website, linked in the description below. I have heard many flat earthers claim this photo and those like it are CGI, photoshopped, fake, green screened, etc. But I'm here to show you that this photo is indeed 100% real. So in this video I will demonstrate why these types of phenomena, like this lunar transit, are exactly what you would expect to see from EPIC's location in our solar system. But first, let's go over some details of the actual spacecraft that has taken these photos. NASA's Deep Space Climate Observatory, originally dubbed Triana, is a satellite that was launched in a Falcon 9 rocket on February 11, 2015. Its primary mission is monitoring solar wind activity to give early indications and warning regarding space weather events such as geomagnetic storms that could damage major public infrastructure like power grids, telecommunications, and even GPS. DSCOVR can give up to 60 minutes of advance warning on coronal mass injections, which are storms of particles in magnetic field, before they actually reach Earth. This satellite is not just for taking pretty pictures of our planet, but has several very important pieces of onboard equipment used to measure not only space weather, but also climate and atmospheric patterns of our Earth. You can learn more about the other systems on board DSCOVR by checking out the links in the description below. So the camera system on board DSCOVR is known as EPIC, or the Earth Polychromatic Imaging Camera. EPIC is a 10-channel spectroradiometer with a 2048 by 2048 CCD sensor coupled with a 30-centimeter aperture Cassegrain telescope, which when you put all of that stuff together just makes a really badass camera. EPIC has a field of view of 0.62 degrees. Remember that because it's going to be important later. And can detect wavelengths between 317 and 780 nanometers, which, to give you a reference, visible light ranges from 400 to 750 nanometers. So this camera not only captures visible light, but also infrared and ultraviolet wavelengths as well. So the primary mission of EPIC is to capture certain properties of our planet to measure over time, such as ozone, aerosols, cloud reflectivity, cloud height, vegetation, and also UV radiation at the Earth's surface. So each one of these channels can capture different wavelengths of light to measure different things, as shown here in this chart. The channels are achieved by having 2 rotating filter wheels with 6 holes in each. 5 of the 6 holes in each wheel have a unique filter while the other hole is left open. The camera shutter has 3 different size slots for capturing different length exposures, each one allowing more and more light to reach the sensor. Alright, now let's talk about where this camera actually is compared to the Earth. So EPIC sits about 1 million miles away from Earth at a point called the L1 Lagrange point. The L1 point allows EPIC to essentially park itself between the Sun and the Earth, and always aiming its camera at the sunny side of the planet. This allows EPIC to capture some stunning photos of the rotation of the Earth, solar eclipses, lunar transits and occultations, wildfires, and even nuclear detonations, although I'd much rather not see that last one. This L1 orbit is not quite stable, so DSCOVR is equipped with boosters that allow it to make minor adjustments to help maintain its position over time. Before we jump over to the simulator, I want to quickly point out a couple of things that you may already be asking yourself. Are the cloud formations that we see in the photo accurate? Where are the stars? Let's take a look at both of those. On this weather tracking website, zoom.earth, I want to point out 3 distinct cloud formations that are easily identifiable by the weather patterns that were actually recorded taking place during these photo captures, July 16th, 2015. You can see 2 hurricanes, Dolores and Enrique, in the Pacific Ocean off the coast of Mexico. And up here off the coast of Oregon, you see this figure 8 shaped void with these 2 little puffs of clouds in it. So now we can jump back over to our EPIC photo and actually see if the same cloud formations for the reported weather patterns are identifiable on that photo. So there you go. Both hurricanes and the figure 8 void match exactly what we saw in actual weather reporting on our website. I find it extremely unlikely that NASA was able to Photoshop these clouds into these photos within the very short amount of time of releasing them on their near real-time website during active weather reporting. Don't you? So the next question, where are all of the stars? This question has been asked many times by a lot of different people on NASA photos, Apollo mission photos, and all kinds of other things. Where are the stars? So as you may have heard many times by now, stars do not often show up visible in photos like these. The main reason for this is simply exposure and dynamic range. Epic adjusts its sensor to match colors and exposure to make it look more like what you would see on, say, a DSLR camera. But because of that, many of the stars are just washed out by the sunlight reflecting off of the Earth. It's just simply too bright to see them. But you still can actually. Take a look. So this is why I've imported this photo into Photoshop. So I'm in my adjustments and I can adjust for exposure here. And I'm going to crank up the exposure and let's see if we can see anything in the background. And what do you know? Here are the stars. They're just simply too dim to see with the naked eye without increasing the exposure of the image. But as you saw, I increased the exposure and these stars actually came to view. And this isn't the only image that I can do this with. I have taken another image of, this is what's called Epic's first light. This is the first actual capture that it got after it was put into orbit in 2015. Okay, so I'm going to do the same thing here. This is a lower resolution photo, unfortunately, but you can still see the effect that it has. Okay, so you can definitely see the artifacts from the JPEG compression around, as well as the compression artifacts from the stars, but they are clearly there. But unfortunately, I wasn't able to find a higher resolution image in a short amount of time, so I went with this one. But nonetheless, you can see how increasing the exposure will actually bring the stars out of these photos. So now let's jump over to the simulator and recreate this image. Okay, so here we are in the beautiful space engine. This is the view if you were sitting on the spacecraft looking at Earth. This is what you would see. I'm going to draw your attention to the bottom right, where you can see our field of view is 45 degrees right now. Do you remember what the field of view was for Epic? 0.62 degrees. So we're at 45 degrees. We are way off of our field of view. Okay, so let's go ahead and zoom in to 0.62 degrees. And there we have it. That is pretty much the view that we get from Epic. Okay, I'm going to draw your attention to the top left here, and we're going to look at the distance here. I'm just under 1.6 million kilometers. Okay, so that's right around 1 million miles away. So I'm going to draw your attention to the bottom left here, where you can look at the date and time. So it's July 16th, 2015, around 1814 GMT. Okay, that's Greenwich Mean Time. So right now I have the camera oriented at the actual L1 Lagrange point, or as close as I know that I can get it. So I'm going to go ahead and play this through, and we're going to see the moon and what it actually does and what it looks like. And we're going to match that to the images that we see with Epic. So this is sped up, right? This is not real time, but you can see the moon actually coming into the field of view. And now it's actually transiting across the Earth. And this looks damn near identical to the image that we saw from the Epic spacecraft. And I'm wondering why that is, right? We have a spacecraft that is 1.6 million kilometers away, 1 million miles, with a very high power telescope with a 0.62 degree field of view. Okay? The moon is crossing the path of the lens in Earth. So it makes perfect sense that this is the image that it would actually capture. Now, I've already proved this software to be extremely accurate with celestial events, with solar eclipses and lunar eclipses and things of that nature. So there shouldn't be a surprise on this photo because this is exactly what we would expect to see from this spacecraft. But I'm going to do a little bit extra. I'm actually going to break our orbit and we're going to pan around and look at what's actually happening here with these orbits. Okay, so let me go ahead and increase my velocity, zoom back out. All right, so what we're seeing here, let me switch back to HDR so I can see what's going on. I'm going to turn some orbits on here. Okay, so we see in red, this is actual orbit around the sun. And what you see in yellow is the orbit around that the moon makes around the Earth. Okay, and the lunar orbit is actually offset from the Earth orbit by 5.15 degrees. Okay, and it wobbles, right? And its offset and its wobble is actually why we get the phases of the moon, which is going to be in a later video. So it makes sense that occasionally their orbits are going to cross paths with cameras and other spacecraft that we have to be able to capture these events. All of this makes sense, and all of this is exactly what we measure in reality. There's no reason to distrust this information. There's no reason. Everything that people have said about this photo is completely baseless. All they have are claims with no substantiating evidence to back them up. This software shows that our model and our current understanding of the orbital mechanics of our solar system are extremely accurate and predictable. So that's all I have for this video. Thank you guys for watching. If you guys have any questions, please leave a comment below. I'll get back to you as soon as I can. Thanks for watching. You guys take it easy.